Welcome back, everyone. Now what we're going to do is we're going to start discussing open quantum systems, which are very useful in many areas of science in which you need to deal with several degrees of freedom, or in which you cannot really define what your system is. So there are many examples, and we're going to discuss what we can do in this case. And this formalism is very powerful. So I hope you enjoy this clip. So our key motivation is related to describing the evolution of a system interacting with an environment. And we are going to go very quickly and talk about von Neumann equation and unitary evolution of density operators. We have already seen density operators, and we know that they are very useful for dealing with systems for which is not enough to consider the evolution of a vector in state space. But if we want to start and if you want to discuss things, we know that if we have a quantum system that is isolated and we can write the state of the system in this form, we have to use the time-dependent Schrodinger equation, and we can solve it, and we can describe how the system evolves. However, real life is a bit different, because in nature, you're going to have systems that are interacting with other systems. So you cannot put a system away in a vacuum and disentangle from everything else. And you're going to have other systems which are going to be what we call the environment. So how are we going to deal with this situation? In principle, you can expand the time-dependent Schrodinger equation to incorporate the whole environment. But this can be crazy, this can be unfeasible, because many times you have too many interacting modes, you have too many particles, you have too many degrees of freedom. Imagine all these people who do like cosmological models where they have like the whole universe, So it can be tricky, and we need to use other resources to consider what is our system and what is the environment. Because in nature, systems are always going to be interacting with the environment. So what do we do? How we deal with these things? So how about factorization? We have seen that many times we can factorize. When you have a compound system, we can factorize the state of the system so that it can clearly see this belongs to subsystem A, this belongs to subsystem B, this belongs to subsystem C, etc., etc., etc. However, if the system and the environment are interacting, they will become entangled. So this is not going to be feasible or possible, because we have seen that if you have a compound system and you cannot factorize the state of the system, is because the system is entangled. If I'm saying, conversely, that the system and the environment are interacting, they will become entangled. So this is not going to be applicable. Otherwise, they wouldn't be entangled. Consequently, yes, so this is the first consequence, that the global state will no longer factorize. So we cannot assign a state vector to the system or the environment individually. So you cannot say this is happening to the state of subsystem A, this is happening to the state of subsystem B, this is, etc., happening to subsystem C, because you're not going to be able to factorize them. And a way to deal with this, which we have seen, is to resort to density matrix formalism, because when you're dealing with density matrices and especially reduced density matrices, you can describe the behavior of subsystem of an entangled system for which you are not going to have a product state, because you can trace out certain characteristics of the subsystem you're not interested in or whose behavior you ignore. And this is done by something very powerful, which are the reduced density matrices. And we need to know how we are going to deal with this. Just recalling, we have seen in previous lectures the density operator, which is given by ρ. And this density operator is a sum over these projectors here. Psi j are associated with a particular outcome, and pj are the probabilities of obtaining this particular outcome. And these projectors are bringing it to that subspace. If you have a pure state, which you can describe by state vector, your density operator is going to be just a single projector. And if you want to compute expectation values of observables, in this case observable O, you have to consider the trace of O with the density operator. We have seen all this, not going to discuss, but just that you have in mind, density operator is Hermitian, it is linear, its trace is unitary, and it is non-negative. So if you calculate the probabilities for any measure, this trace also has to be non-negative, because you don't have negative probabilities, and you can clearly see that they are associated with probabilities for any measurement. So if you write now in terms of an orthonormal basis phi j, we have also discussed that you can put closure relations here, and you're going to have this as a sum over jk, whereby these are the bases, these are indices associated with the basis states, associated with this type of operator phi j, phi k, and rho jk are the matrix elements of the operator between phi k and phi j, rho jk. And for compound systems, if you consider now a bigger system consisting of several subsystems, or at least two subsystems, in this case two, you can write rho as these expressions. So here we have compound states, AJ, BK, AL, BM, and they are associated with subsystems A and B, A associated with A and B with B. They're defined as tensor products. We have now sum over 4 indices, and we have then this matrix element here, rho JKLM, whereby this is the density operator between states AJBK and ALBM. This we have seen as well. And if you want to compute reduced states for entangled systems, what do you do? Well, you cannot separate the state vectors of individual subsystems. So you compute partial traces, because when you do that, you can erase the contribution of a subsystem. For instance, here, if you compute trace over A of rho, you trace out system A, and you get this reduced density matrix. And if you want to compute expectation values in this case that act on B alone, instead of considering the whole rho, you consider rho B, in which the dependence on A has been traced out. And the same is going to hold for tracing out system B. So you have this reduced density operator, which you have established by tracing out B. And if we talk about time evolution of rho, which is our density operator, if at a time t equals 0, the system is in this state, what we can do is we can evolve psi t. So we know that psi t would be ut, taking the system from 0 to t applied to phi j, psi j, which is your initial state. And you can do the same for the corresponding dual vector, but in this case you would have u dagger t. You can show then that your whole t is going to be whole 0, but sandwiched from the left with ut and from the right with u dagger t. And the important thing is that if you are evolving these, you can see that whatever is mixed is going to remain mixed. Whatever is pure is going to be pure. Now, we are going to talk next about the von Neumann equation. And this is an equation which is useful for mixed states. And it's the density matrix formulation of the time-dependent Schrodinger equation. This is important for us at the moment because if we are going to discuss open quantum systems focused on reduced density matrices and density matrices, we need to have a whole framework which we can use to be able to operate. Now, in this other whiteboard style derivation, what I'm going to do is I am going to derive the von Neumann equation, which is useful for us because since when dealing with open quantum systems, we're going to use the density operator a lot, we need to have some way of writing the time evolution of a system in terms of our density operator. So we're going to start by computing the time derivative of rho t, whereby this is the density operator at time t, and this is going to be ut rho 0 u dagger t, just using the standard unitary time evolution that we know. If we apply then the derivative of a product, we get that this is gut dt rho 0 u dagger t plus ut rho 0 d dt u dagger t. Now we know that u, the time evolution operators, and also u dagger, that they obey the time-dependent Schrodinger equation, right? So we're going to use this fact. So we're going to use the ut dt is minus I h bar, minus I multiplied by the Hamiltonian divided by h bar ut. And for u dagger, we're going to have then u du dagger t dt is going to be I goes to minus I. Hamiltonian is assumed to be Hermitian, so it's not going to change. And we have now, it has to be the other way around. Sorry, guys. So this is going to be u dagger t h, which is equal to h dagger here, at least in our framework. So let's put this here, and we're going to find that so inserting in this expression here, we're going to find that t rho t dt is equal to minus I h ut rho naught u dagger t. Don't forget the H bar. Hang on. Move sometimes, you know. Don't forget over H bar plus I over H bar, you'd see Ho 0, Udaga T H, which means that we can write this looking at this expression. You can clearly see that this is Ho at a time T. This is Ho at a time T. So we'll be able to write this as d Ho T dt equals to minus I divided by H bar, H Ho T minus Ho T H, which is the commutator of H with Ho T, so that I can say that d Ho T over dt is minus I H bar, commutator of the Hamiltonian with Ho T. And this equation is the von Neumann equation and is going to be quite useful for us when dealing with open quantum systems. Next, we're going quickly to see again once more purity of a state. We have discussed this briefly, but we know that if we take a measure of how pure a state is, you have to take the trace of Rho squared. This is quite a useful quantity because it is relatively easy to compute once you know Rho. And we know that a pure state is always going to have purity 1. So that is the idea. You take the trace of Rho square, which at the end of the day is going to be the trace of Rho because it's going to be a single projector, and you can calculate and just that this is going to be 1. For a mixed state, the trace of Rho square is smaller than 1. So this is a good measure because you know that when the purity is 1, your state is pure. Otherwise, your state is entangled with something. This doesn't tell you with what the state is entangled, but it is entangled with something. And one can show that the purity is invariant under unitary transformation. And this is something that is important for us. We're going to take some time deriving it, but the key idea is that the trace of Rho T square or the purity at a time t is going to remain the same as the purity at your initial time 0, which means that one cannot create a mixed state from a pure state just by having time evolution alone. If you just have unitary time evolution, you're not going to be able to do that. Whatever was pure is going to remain pure, and whatever was mixed is going to remain mixed, because the purity is going to be invariant under unitary time evolution. So you have to have other types of evolution to be able to change the purity of your system. So in this whiteboard type derivation, what I would like to show now is that purity remains invariant under unitary time evolution. And this is something that is quite important because it's going to lay the ground to the fact that you need another types of evolution to make pure system mixed or a mixed system pure. So just to recall, what we would like to show is, we would like to show that purity of a system at a time t is equal to the purity of a system at a time 0, whereby we're using here the notation we know for purity, which is the trace of the square of the density operator. So let's consider what we know. We know how to take a density operator from a time 0 to a time t. So we know that rho t is ut rho naught u dagger t. So here we used the time evolution operators from 0 to t. It was just a shorthand of t of ut naught, but I neglected the naught, so that you know what I'm doing here. And we can also immediately say what is going to happen with the purity and also with the square of the density operator, because we know that rho square t is rho t, where I apply this twice. So let me use then this expression that we have here, and I can write rho square t as ut rho 0 u dagger t ut rho 0 u dagger t. Now note that u is unitary. We know that the time evolution operator is unitary. So this is going to be the identity operator. Therefore, we can say that rho square t is ut rho 0 times rho 0, which is rho square 0 u dagger t. So actually, this is something we expected, but I'm showing just that you can be really sure. You can see that this whole square operator evolves like every operator would evolve under unitary time evolution, correct? So now what we need to do is let's compute the trace. Let's see what happens to the trace. So the purity is the trace of rho square t, correct? So this is the trace of ut rho square 0 u dagger t. Now, what is really nice about the trace is that we can use cyclic invariance. So if we using cyclic invariance, this R looks strange. We know that trace ABC is equal to trace BCA. So what can we do about it? Well, we have three operators, don't we? Call this guy A, call this guy B, call this guy C, which means that trace ut whole square 0 u dagger t can be written and is equal to trace whole square 0 u dagger t u. Let me move this a bit. ut. Now we know that these operators unitary, So we can write this as unity operator, which then gives you that trace of whole square t is trace of whole square u, which proves our assertion that purity is invariant under unitary evolution. So next, we're going to talk about ways of making the evolution of a system non-unitary. And we're going to discuss what kinds of formalism we'll be able to use in this case. So that in principle, you can incorporate classical randomness, or you can incorporate entanglement with other systems in your system's evolution. I hope that you enjoy the next clip. See you soon.